Okay, folks, I want to look at doing the pre-work. This is the pre-work for section 2.6 on continuity. So the first thing we're asked to do is graph f. There's no new material in this, so what I'd like you to do is pause the video and sketch a graph of f of x. So if you have any trouble with this, we did something like this in section 2.3. Actually, we kind of looked at each one of these in section 2.3. So review your 2.3 notes for the graphs of these functions, and then give your best shot at graphing this. So go ahead and pause the video, and we'll resume in a moment. So the graph of this function should look something like what I've sketched here. If you had any trouble with this, go ahead and pause the video, copy down the graph. But don't beat yourself up. But do know that each one of these, this is a pretty large graph, but each one of these pieces is fair game to ask you to graph. So if you're having trouble, feel free to come by and see me during office hours. Okay, so we notice that for this graph, there's a lot happening at, say, at -1, and at 1, and at 3, and at 4. These are kind of the interesting points on this graph, and we'd like to be able to utilize some better vocabulary to describe what's happening with the function at those points. And so what we need to introduce is this new idea of continuity. And that'll enable us to explain looks like I noticed I missed a point here, so let's fill it in. That'll enable us to explain what's happening with this graph a little bit better. So folks, notice I neglected to fill in the value 1 there. Okay, so here's the definition of continuity. Let f be a function. If the limit as x approaches a of f of x is equal to f of a, then we say that f is continuous at that a value. So let's just clarify this, and notice, whenever we take the limit of a function, we write the function of f of x here, right? We don't write f of a. But the limiting value here is a. We are approaching a from, I guess in this case, either direction, and we're saying if this limit exists and it equals the same thing that we get when we plug in a into the function, then we're going to say that we're continuous at x equals a. So this is a nice compact little statement right here. The limit as x approaches a of x equals f of a. That's our definition of continuity. So we're going to say that when this is true, f is continuous at a. Well, this definition actually requires 3 different things to happen. First of all, it requires that the limit as x approaches a of f of x must exist. It requires that f of a must be defined. And further, it requires that they equal each other. So all 3 of these things need to exist in order to be true in order for us to say that f is continuous at some value x equals a. So let's look back at our function here that we sketched. Okay, so let's see if we can do this. I have to jump up and down in the view. The above function is not continuous at x equals -1. So let's look at this. Yeah, it's not continuous at x equals 1. How come? Because the limit at x equals 1 doesn't exist. So if the limit doesn't exist, it's not going to be continuous there. It's also true that f of a, I think I wanted the word and there. It's also true that f of a is undefined. So let me say f of -1 is undefined there. So the function's undefined at -1. That's one reason why it's not continuous. And the second reason is that the limit doesn't exist there. So as far as checking that you've met the first 3 hurdles, well, you failed step A, you failed step B. It's not even worth checking to answer the question for step C. So it's certainly not continuous at x equals -1. The above function is continuous at x equals 1. How come? Well, because the limit exists. Check that. As I approach 1 from the left, I'm getting out these y values here. and as I approach 1 from the right, we're approaching. So yeah, sure enough, as we get closer and closer to x equals 1, the y values are approaching -1 for either direction. So we would say that the limit exists. F of 1 is defined. What is f of 1? Well, we're told that if we plug a 1 into this function, it's supposed to output a -1. So f of 1 is defined. Okay, careful, folks. Again, when I originally sketched this graph, I forgot to fill in that hole there. Okay. And they agree. So let's just check that that's so. So what is the limit as x approaches 1 for this function? Well, regardless of whether we come from the left or the right, we ended up getting -1. And f of 1, we saw just from the definition of the function, was -1. So the limit as x approaches 1 of f of x equals f of 1. So this is exactly what we need to show in order to show that we're continuous at a point A. Okay. By the way, this function is continuous at a lot of other points here too. So for instance, any point where I've just drawn these horizontal segments or this linear segment, it's going to be continuous there because for instance, at x equals 5, yeah, the limit exists, the functional value exists, and they agree with one another. Okay. Again, the above function is not continuous at x equals 4. Why is that? Well, at x equals 4, does the limit exist? Yes. Even though the limit exists at x equals 4, f of 4 is undefined. And we see that, the function was, we didn't give a definition. What do we do if f equals 4? Well, there's, of our different pieces to the, our different rules to the piecewise function, we didn't give a rule for what happens when x equals 4. So f of 4 is undefined. The above function is not continuous at x equals 3 because even though the limit exists, and even though f of 3 exists, let me say the limit exists, let me add at x equals 3, even though the limit exists at x equals 3, and even though f of 3 exists, they don't agree, since, well, what's the limit as x approaches 3 of f of x? Well, in this case, let's see here, as we approach 3, regardless of my direction, as I approach 3 from the right, my y values are approaching 1, or as I approach 3 from the left, my y values are approaching 1, and so the limit proper is 1. Okay. But f of 3, by the rule of this function, says, hey, when x is 3, we're going to output a -1. So f of 3 equals -1, and we can see that the limit as x approaches 3 of f of x, that was 1, and that certainly does not equal f of 3. So take a look at these examples. We've had one place where, it could potentially be discontinuous. We were joining two parts of a continuous function at x equals 1, but we saw actually we are continuous at x equals 1. But at x equals -1 or x equals 3 or x equals 4, we said that the function was not continuous there. And each one of them is sort of for its own reason. Here, the limit doesn't exist. Doesn't matter whether the functional value exists. The limit doesn't exist, so it can't be continuous there. Here, the limit exists, but the functional value didn't exist, so we're not continuous at x equals 4. Here, both the limit exists and the function's defined when x is 3, but these two don't agree with each other, so we're not continuous at x equals 3. So take a look at those, reread through them, and make sure they make sense, and we'll see you in the next video.